Hey guys, welcome back to the show. I hope you had a really great day off yesterday. We're back now looking at differential calculus. This is our last week before we go into analytical geometry next week. Just a reminder that you can download our app. It's available on Android and iOS. Guys, I really love this app. They give you a whole bunch of questions on there that you can actually look at before you write your cycle test, before you go into your exams, and it's free to download. All the concept videos as well as the career videos and all the content that plays before the show, you can have a look at it again once more before you look at your content, before you write your tests and exams. We're going to have a great question now today from Terry. It's based on maximization and minimization problems. Let's have a look at what Terry has to ask us.
Hi Tenfold, my name is Terry. I'm from Mpumalanga and I need help with this question.
Okay, thanks for that question, Terry. I'm actually going to down over here for us so we can have a look at what it says at home. When it comes to doing your calculus exam, guys, you got a maximization and minimization problem in every single final exam that you write. And you always have to do some sort of derivative that you can find a maximum or minimum. The question from Terry today says the following. It says here that a box is made from a rectangular piece of cardboard 100 centimeters by 40 centimeters. And by cutting the shaded areas and folding along the dotted lines as shown in the diagram above, we get this box. Okay guys, so if we have a look at this piece over here, I don't know if you guys have ever done this before, where you make like a little net for yourself and you cut out your corners and you fold them up and it makes a nice, really nice box you can pack all your stuff in. So they've done the exact same thing here, and now they've applied some maths to it and asking us, well, what can we do and see, how can we maximize this volume of this box? So the first question says the following. So if we have a look at it, the question says, express the length in terms of the height h. Okay. So if we have a look at this diagram, we've got h, my length of my box, and we've got another h, and the total length of this cardboard on the side is equal to 40 centimeters. So we can write a little equation for ourselves that says the following. We can say that L plus, now look at this guys, we've got h and we've got h again, so that's going to give me 2h, and that's going to equal to my total on the side, which is going to be 40 centimeters. And that's going to be 40 centimeters. And we're asking, or express the length in terms of the height h. So we can then say that L is equal to 40 minus 2h. Okay, so that's a nice little thing that we're probably going to use it later on in the questions. But if you get that wrong, guys, you will get some follow-on marks later on when you start going into your tests and exams, and hopefully you won't make silly mistakes. Let's go have a look at the next part of the question. The next part says the following. It says, hence prove that the volume of the box is given by V equal to H multiplied by 50 minus H multiplied by 40 minus 2H. Okay guys, so if you have a look at what our volume is over there, we've only got it in terms of H's. But if you go back and look at our diagram, we've still got our diagram, it's in L as well as in B for our breadth. So we only want our volume to be in terms of H. So we're going to have to do a whole bunch, or we're going to have to make up those little equations again like we did in the previous question to try and get rid of our breadth, which is B, and our L, which is our length. Okay, so we're going to do this by looking at the following. We're going to say, well, my volume for a rectangular prism is equal to my length multiplied by my breadth multiplied by my height. And we already found out in our previous one that my length is equal to, let's make sure I get this right, my length is equal to 40 minus 2h. 40 minus 2h. So if we go back and look, we want to now find my breadth in terms of h as well. So if you look at my breadth over here, we've got that my total side is going to be 100 centimeters, and we've got h plus my breadth plus h and my breadth again. So we can write another equation for my breadth and my height. So we're going to say 100 is equal to 2h plus twice my breadth. And like I said, guys, like I said earlier, if we look at our equation that's been given to us in our volume, we only have it in terms of h. So we want to try and find what h is in terms of all these other variables that we've got with us. So if we take this, we're going to say then that 100 minus 2b is equal to 2h. And if we divide both sides by 2, we get 50 minus b is equal to h. Okay, and this part of here is going to be another side for my breadth. So we're going to substitute that in. We're going to say my breadth is going to be equal to it's going to be 50 minus h. Now if we've got to plug both of these pieces into my volume equation, we get the following. We're going to get my volume is equal to my length, which we have as 40 minus 2h. 40 minus 2h. And then we're going to get my breadth, which is going to be 50 minus h, multiplied by my height, which is then h. And that's exactly what we have over there, guys. Okay, the order just a little bit different, but it is exactly the same. Okay, let's move on to the next part of the question. It says here, for which value of h will the volume of the box be a maximum? Okay, so for which value of h will it be a maximum? Okay, guys, when it comes to maximization and minimization problems, to find the maximum or the minimum, we equate our first derivative equal to 0. So to get that, we first need to find an equation that we can do the derivative with, and then from there equate that to 0. So if we go back and look at my equation quickly. So I'm going to take this equation over here, and I'm going to multiply it out. So let me get it down over here quickly. Whoops, wrong way. So we're going to have V is equal to 40 minus 2h multiplied by 50 minus h and multiplied that by h. Okay, so guys, to do the derivative on this, we first want to put it in terms, well, we want our terms to be all separated. So we're going to multiply 40 times 50 is going to be 2,000. Okay, and then we're going to have, guys, I want to go back here quickly. It's 40 minus, yep, that's correct. Okay, that's going to be 2,000 minus 40h. And then we're going to have, it's going to be minus 2 times 50. That gets me minus 100h. And then we're going to have minus 2h multiplied by another negative h. That's going to give me positive 2h squared. And all of this is then going to be multiplied by h. Let's do that step one more time, where we distribute my h in. That gets me 2000h minus 40h squared minus 100h squared plus 2h cubed. Okay, so far it's straightforward, guys. Let's just simplify this a little bit more. We're going to end up with 2h cubed, and minus 40 minus 100 is minus 140h squared plus 2000h. Okay, guys, so now we've got our formula for our volume. It's all our terms are separated. It's not a single, or it's not terms multiplied by one another. So now it's really easy to do the derivative on our formula that we've just found now. So if we've got to do that, if we find my volume, which is going to, well, if you find the derivative of my volume, we're going to get 6h squared minus, that's going to be 280h plus 2000. Okay, guys, so that's what we have over here. Now, when it comes to doing this, we can either use my quadratic formula, or we can, if the factors are nice that we can find, we can then plug it into our, we can actually use some factors that help us get to our factors to solve for h in our first derivative. So if we equate my first derivative equal to 0, I'm just going to go off quickly, and we're going to be back just to get my calculator. This shouldn't take too long. Sorry about this, guys. Actually, you know what, guys? Just give me my calculator here quickly. You know, these things happen when you're working on television. There, I got my calculator. Awesome stuff. All right, so I got my calculator over here, and let's have a look at what we're going to do. Let's close that. Okay, guys. So now we're going to take all our little terms, and we're going to plug them into the calculator, and we're going to solve for our h. So what I'm going to do is, what I like to do is I like to say 6, and I'm going to go shift store as A, and then I'm going to take my other value, I'm going to say minus 280, shift store it as B, and my last value is going to be 2000. I'm just going to say 2000. I'm going to go shift store it as C. Okay guys, so now we've got all my values stored in the calculator. So what I can do is I can now plug them into my quadratic equation. So it's going to be quite straightforward. I'm going to have minus B plus the square root of B squared minus 4AC and divide that by 2A. Okay, so if we get that, my first value is 37,86. Okay, so if we equate this to 0, we actually end up with V prime equaling, it's going to be H minus 37,86. And my other one is going to be, now this is very clever, we can just go back and delete that. And we're left with 8,80. So it's going to be H minus 8,80. Okay guys, so now we've got our two values for H. They want us to find out which one's going to be the maximum, which one's going to give the minimum. So now we've got to be very careful about this. We've got two values. We've got one which is 37 and we've got one which is 8. But guys, don't be fooled by taking the largest value and saying that's a maximum. No, that's not what you got to do. Okay, if we have to draw out a cubic function, now my cubic function is going to be positive. So you can see over here, it is a positive cubic function. And the way my positive cubic function goes is that we're going to have a maximum at this point over here. Now, if this is a timeline or a number line, this is going to be the value of 8,80, and this value over here is going to be 37,86. And this here is going to be my maximum. So therefore, we can say this is maximum when H is equal to 8,80. Okay, lovely question. Guys, it gets you thinking about all these concepts that are going to be asked in your exams and your tests. We're going to take a quick break now, and then we're going to be back with Philippa on some more of your differential calculus questions. Guys, stay tuned.
I work here at BIOMEDICAL Technologies. I studied mechatronics engineering at UCT a number of years ago. It was quite tough for me. I hadn't done a lot of the extra maths and some of the extra sort of courses like drawing and that some of the other students had done. So I found it quite a challenge, but I really enjoyed it, and it was just good to get some hands-on experience and to be really sort of stimulated. We decided we wanted to get involved in some of our own projects. So we started BIOMEC a number of years ago now, and we specialize in biomedical engineering, but also various other industries. This is a device called Pulse. It's a pump that's used to pump synthetic blood through a cadaver for surgical skills training. So this is really important for surgeons to practice their surgical skills on a subject that's as close to a living patient as possible, without it actually being a living patient. You start off usually in an R&D phase, so often the client has an idea, but they're not always sure how exactly to implement it. So one of the first things you do is your research and development. Specifically with medical type projects, there's often a lot of unknowns which you need to investigate. So you do your research and you do your experiments, and you come up with a plan to prove a concept. And then once you have that in place, then you're usually a bit more in a better position to put a specification together, or what we sometimes call an architecture. So you develop what we usually deliver in a document, which basically says these are the criteria that my product needs to meet, and once we've done that, then we can develop a high-level architecture, which is pretty much a high-level view of all the subsystems and systems in your project and how they're going to fit together. And then once you've done that, you sort of dive into the deeper design, and the projects we do, that there's ranges from electronics, mechanical, software, industrial design, so you sort of do those what we call modules in a detailed design level. Throughout the project there are a number of other phases, so you've always got to manage your risk and you've always got to manage your quality. So those sort of parts of a project sort of run throughout the project, specifically for medical devices, which we do a lot of. Your risk management and your regulatory management and your quality management runs throughout. So math is actually a very important part of what we do. It comes into a number of aspects of what we do. So to start with, for example, we do a lot of maths in our mechanical design. It comes into our strength calculations, particularly. So obviously, when you develop a mechanical system, it usually has to have some sort of performance, mechanical performance, and also support often a mechanical load. So there will be a lot of calculations up front that we do to ensure that that happens. This uses GPS coordinates to deploy fertilizer in an orchard. It's used in the agricultural industry. It also plots its trajectory on a user interface for the user to see via the cloud. Whoever's running the system can see where the fertilizer's been exactly. And yeah, it's got electronic systems in it, it's got mechanical systems, it's got a number of motors that actually deploy the fertilizer, and it's obviously got quite a lot of code behind it that controls the system. So we do quite a bit of mechanical calculations for the shipping industry. So there's, you calculate the strength of various mechanical materials, and so yes, there's a bit of calculus involved there. There's some subjects that are more easily accessible now compared to when I was at school. So there's now an engineering design course, which is a really good one to do. There's IT, which is a lot more developed and accessible than it was when I was at school now. So learning to code and do all of that is really important. And then, yeah, I mean, those are the main courses. Chemistry is useful. I mean, it comes into even what we do. We're not a chemical engineering company, but it's a good background of knowledge to have, and we do sort of look into that from time to time. Basically, what this little device does is it has an accelerometer on it, which measures the acceleration of the head about the center point, and that information, that data, can be collected and used to calculate the likelihood of a concussion. I think I get the most excited when we're doing a really nice medical project, because that's sort of when I was little, I had this dream of doing medical type work. I didn't necessarily want to be a doctor because I enjoyed the pure maths and the design side of things. So I kind of always envisioned working in the biomedical space. So that's really what gets me excited, is when we're working on projects that really gonna help people.
Hey guys, and welcome back. Hopefully you enjoyed that career video. I really loved it so much because I actually tried my hand at a medical career before I became a teacher, and it just did not suit me. So what she said about wanting to do medics but also wanting to do pure maths at the same time really hit home. So guys, just pay attention. Make sure you know that your calculus is not just for weird graphs and stuff inside your classroom. You can actually use it for really cool things like helmets that prevent a concussion. But yeah, anyway, we're going to jump into our next question. It's from Courtney and Oratile. Let's see what they need some help with.
Hi Tenfold, my name is Oratile.
And my name is Courtney. Can you please help us with this question?
And once again, I get the cubic function because someone doesn't like me upstairs, but it's cool. We're going to jump right into this question because it's actually a really good question. It tests kind of your remainder theorem, your factor and remainder theorem, which is really cool because now we're seeing like a crossover between our different maths areas. So let's jump into this question. It's a really great one. It says the graph of f of x is equal to negative x cubed plus ax squared plus bx plus c is sketched below. Okay, so that's what this graph over here is. It says the x-intercepts are indicated. So we have an x-intercept as x equals 1, x equals 2, and x equals 4. Okay. Firstly, it says calculate the values of a, b, and c. Okay, so guys, if you remember your factor and remainder theorem, If you have a factor that is a perfect factor of a cubic function, it means that if you multiply that factor or you substitute it into that cubic function, you're going to get a value of 0. Okay, so if you remember, guys, if you're given a factor, you write it as x minus that factor, and that's one thing that makes up that original cubic function. So if we have x-intercepts, it means that the y0 is 0, which means that that x-intercept is a root of that equation. If you have x-intercept multiplied by x-intercept multiplied by x-intercept, you're going to get the equation of your cubic function. Okay, so when we're trying to find this cubic function, we can say the first intercept is -1, or it's 1, so that means that the factor is x minus 1, multiplied by the next intercept, which is x minus 2, multiplied by the next one, which is x minus 4. Okay, because at x equals 4, y equals 0, so that means the whole factor is x minus 4. Okay, so now we can simply multiply this out. If we multiply the two brackets out, the first two, we get x squared minus 3x plus 2, and the last bracket stays there. If we continue to multiply out, we get x cubed minus 4x squared minus 3x squared plus 12x plus 2x minus 8. Okay, so now let's just simplify with like terms. Get x cubed minus 7x squared plus 14x minus 8. Okay, so that is our function. But guys, there's something wrong here, because if you look, this is essentially a reflected function, because this leading coefficient of x cubed here is a negative. Okay, so we've now found the equation of negative f of x over there. So in order to find something that has a coefficient here that is negative, we need to multiply the whole function out by negative. Okay, so that means that the function is given to us as negative x cubed plus 7x squared minus 14x plus 8. Okay, so now we need to find those coefficients. So we see that a is the coefficient of x squared, and then b and c are the next two coefficients. So that would be a, b, and c. So we can say a is equal to 7, b is equal to negative 14, and c is equal to 8. Simple, simple, simple. Next thing, it says calculate the x coordinates of a and b, the turning points of f. Okay, so we're trying to find these coordinates here. Now guys, if you remember what we've been talking about, if you have a turning point there and there's a tangent at that point, it means that that tangent is horizontal. It's going to go flat, flat, flat. And what do we know about horizontal lines? Their gradients are 0. Okay, so if you remember with your differential calculus, the moment you differentiate, you're trying to find the gradient of the tangent at that point. So if I find the first derivative and make it equal to 0 here, I can find the equation or the coordinates of the turning points. Okay, so we find that f of x is equal to negative x cubed, let me double check, negative x cubed plus 7x squared minus 14x plus 8. Okay, so if we find the first derivative, it'll be negative 3x squared plus 14x minus 14. Okay, so now remember the gradient is equal to 0. So if we make this first derivative equal to 0, we can find the x coordinates of those turning points. Okay, so I'm going to multiply out by a negative because I don't like that negative leading coefficient. But let me just fix that because I'm talking nonsense. And that'll be plus 14 is equal to 0. Okay, so looking at this coefficient of x squared is kind of icky. I don't like it when it's not 1, so I'm going to be lazy and use the quadratic formula. So we bring up the calculator, which Julian nicely opened up for us. So x is equal to negative b, which is 14, plus the square root of b squared, minus 4 multiplied by a, multiplied by c, all over 2a, which is 6. So we get x is equal to 7 plus root 7 all over 3, or x is equal to, well, that would be simple because remember over here in the quadratic formula, it's a plus or a minus. So the second one would be 7 minus root 7 over 3. And that answers the question because it said, calculate the x coordinates of A and B, the turning points. Okay, so let's just go back and check our diagram quickly. A would be the smaller value and B the larger value. So over here, this would be B, and that would be A. Okay. Lastly, it says for which values of x will the first derivative be less than 0? Okay, well, we've just found these are the values for x that make the first derivative equal to 0. So when x is equal to 7 plus or minus the root of 7 all over 3, the first derivative of x is equal to 0. So that's saying that x minus 7 plus or minus root 7 over 3 is equal to 0. Okay, now we're trying to find when it's less than 0. Okay, so if we take this over here and we bring it down here, we can simply say that x needs to be less than 7 plus or minus root 7 over x. Because if x was equal to this, it would be, or x minus this is equal to 0. So if it's less than that, it means it's going to be less than 0. So let's look and see if this makes sense on our graph. Okay, so I'm going to go and double check what this value actually is. Okay, so 7 plus or minus the root of 7 over 3 is equal to 3,215, which is roughly around here. So that was that turning point. And then the other one would be this over here. Okay, so let me see if I'm actually making sense with what I'm saying. If I look at x is less than the first value, so let me look at this first value here. That value is this one over here. So if that is less than there, it doesn't really make sense because the graph is increasing there, okay? And remember, guys, if this is less than 0, it means that the original graph is decreasing. Okay, so let me see if I was making sense. The graph is decreasing here. So that means that the x value needs to be greater than that one. Okay, so I was talking rubbish there. Let me make sure I qualify this. So x needs to be greater than the bigger number that we said there. And over here, the graph is decreasing up until this point here. So that's that second value that we found. So x needs to be less than that second value that we found. I know I started going on a tangent and a ramble, guys, and I know that I didn't make sense, but hopefully you understand from my correction. Remember, guys, first derivative dictates where the original function is increasing or decreasing. So if you find the first derivative of the graph and it is less than 0, it means that the original cubic function is decreasing. First derivative negative, decreasing. First derivative positive, original function is increasing. Okay, so hopefully this has helped you understand a little bit more of your cubic functions. Pretty sure it's the last one we're covering for differential calculus, so unfortunately that's us for cubic functions for now, but thank you so much for sending in your question, guys. Thanks again to Liberty for sponsoring us. We really love doing this and sponsoring our app. If you liked that career video, guys, download our app. We've got some great videos on there, including career videos and a whole lot of other lessons and stuff. So really download that app. It's really a bang for your buck. For now, we're going straight into an ad break so you can let your brain just chill out for a little bit, and then Julian will be back afterwards. So stay tuned.